Okay, hallo, ich heiße Jakub, ich komme aus Polen und ich werde über G1GC sprechen. Unfortunately, that's all I can say in German, except quoting Rammstein lyrics, but I think it's not something you want to hear in the next 50 minutes. So I will be talking about the garbage first garbage collector, so something that was introduced a few years ago, and the garbage collector implementation that is going to be a default for Java 9, which is coming in a few months. You can find my Twitter handle here, so feel free to tweet as much as you want. So, few words about me at the beginning. I'm a professional software developer for all over 12 years, so I've started in 2004, and now I'm co-founder of DevSkiller and CodeArty. DevSkiller is a platform which allows you to verify coding skills of the candidates that you want to invite them for an interview. So before inviting them for an interview, which takes your time, you can ask us to provide an online evaluation, which is using the target libraries which you use on a daily basis. So if you're using Java, Maven, and MongoDB, we can test candidate in a real environment using Java, MongoDB, and a Maven. And also I run a CodeArty. It's an agile software house when we are creating some small Java projects, and we provide also consultant services for our clients. Okay, so that's all about me. Now I want to know a little bit about you. So who of you are Java developers? Okay, and who have ever before analyzed the garbage collection logs? Okay, and some of you are involved on JVM tuning on a daily basis. Okay, so one person. Okay, so why should you spend the next 50 minutes in this room? Okay, why all this mess? Simply because our application needs memory, and the memory is limited. Okay, the memory is cheaper and cheaper and cheaper, but we are using it a lot, so it's still limited for us. And as a Java developer, we are generally too lazy to manage the memory manually, like you do in, for example, C++ or C languages. So we want the garbage collector to do our work, okay? And garbage collector has a limited performance, and he needs to stop the word to reclaim the memory, okay? So why do garbage collector need to stop the word? Basically, there are two kinds of garbage collecting algorithms. One is the scalar algorithms, and the second is a vector or tracing algorithms. Okay, scalar algorithms are relatively easy. They act as reference counting operators, which means if you are assigning some object to a variable, then you are increasing the reference count to 1. So one reference is pointing to this object. If you will null this variable, then nothing is pointing to this object, so the reference count is equal to 0, which means this object is now a garbage. Okay? So do you have an idea why such easy algorithm and such efficient algorithm cannot be used in Java? No, there's no problem in concurrency with this. Okay, so we can imagine the situation when there is something which looks like a snake eating its own tail. Okay, so I have object A pointing to object B pointing to object C, and object C pointing to object A. Okay, so there are 3 objects. Each of those objects has one reference, but all this part of our memory is not referenced from outside of this thing, and this thing is called an isolation island. Okay, so we are not able to track such islands in by static algorithms. And in Java, this isolation island can be some, let's say, object retrieved by Hibernate from database, and it can take like 1 gigabyte of memory, okay? So we are not allowed to just ignore it, okay? So yes, Scala algorithms has big advantages as they are really fast, really efficient, but as long as they are not able to track those isolation islands, we have to use vector algorithms. And vector algorithm is something that we also call the tracing algorithm. So it traces the relations between different objects. So at the beginning, the vector algorithm needs to start somewhere, okay? So it starts from the roots, and in garbage collection, the root is something that is it's alive by default from definition, okay? So if something is assigned to a variable or to method parameter, if something is used like a mutex or monitor or something like that, we are sure that this object is live, okay? Because if I'm inside the method, and I have a variable in this method, this variable is reachable, okay? So all those objects are treated as a garbage collection route. So at the beginning, we need to find all garbage collection routes, and that's the first step of a vector algorithm. The second step is that we iterate over each root object, and for this root object we are marking all referenced objects. So I am a root and I'm pointing to you and you, so I'm going through all these relationships and I'm marking all objects as live. Then for all objects that are available in memory, I'm iterating over them, and if this object is marked as reachable, then I'm unmarking this object to prepare it for the next garbage collection cycle. And if this object is not marked as reachable, then I'm removing this object and I'm reclaiming the memory. Okay, so basically it looks really simple. So what's the problem? Yeah, the problem is that in our application there are millions of objects. Okay, and those millions of objects has to be scanned and processed by a garbage collection. So when you implement such algorithm, it will be able, of course, to free your Java memory, your heap memory, but it will take dozens of seconds. Okay, it's not acceptable when we are talking, for example, about the web applications. Okay, if user clicks someone like add product to the cart bin, and then he needs to wait 20 seconds until the garbage collection is finished. Okay, it's not something that we want to do in our users. Do you have a question? No? Okay. So there are generally a lot of tricks that garbage collector needs to do to be able to finish this work in a limited amount of time. So limiting this stop the word phase, which means the phase when all application threads are stopped and the only thing that is going on is a garbage collection. So the one of the most key optimizations done by garbage collector is something that we call generational hypothesis, which means that it's based on something that is called the infant mortality. Okay? If you bring or refresh your memory and bring back childhood memories, you will probably agree with me that we are all here due to unbelievable fortune. Yeah, if you take a look at this image, it's real luck that this girl still exists. Okay, and we try to do the same in Java world, which means that young objects are very likely to die soon. Okay, and on the other hand, when the object is, let's say, pretty old, it's probable that this object will live long time more. Okay, so if we know such things, that young objects will probably die soon and old objects will live forever, almost, then we can try to treat them in two different ways. Okay, so young objects treated by algorithm A and old objects treated by algorithm B. Okay? And do you think that this generational hypothesis is something that applies to all kinds of applications and all kinds of objects? So when it's false. Okay, so could you give me an example of an object for which the generational hypothesis does not apply? So the object which after the instantiation, I'm pretty sure that will live for at least 1 hour. And if this object is living for 59 minutes, I know that it will be reclaimed immediately. Okay, so let's think about the HTTP session. Okay, HTTP session, if it's created, it will be probably live for at least the expiration time. Okay, caches as well. If you add some element to the cache, okay, it's for example using the time to live for 60 minutes. This newly created object will live in this cache for 60 minutes. And if this object is 59 minutes old, then it will be reclaimed in a minute, okay? So generational hypothesis, it's not a golden hammer. It's not solving all the problems, but it's still some kind of optimization, okay? If we think that there are two different generations living and working outside of each other, then comes the problem that how can we process the single only the single generation while there still can be some relationships between those generations, okay? So we can imagine the situation when some old object is pointing to a newly created object, okay? Standard situation, I have a map, standard Java hash map, okay? This map was created when I started my program. And now I'm adding some new objects to this hash map, okay? Which means the new object is inside the hash map, so the map is pointing to a newly created object. Hash map lives in the old generation because it's a really old object. This newly created entry is in the new generation, but there is a pointer, okay? So to be able to process the young generation, so those new objects group, I still have to check if there are no old objects pointing to my new one, okay? So all my optimization I can now throw away because I still have to process the whole the other generation to find out if there are no relations to the other generation, okay? And that's something that is that the Java developers is overcome with something that is called the card table, which means that the whole old generation is divided into slices, and each slice is taking 512 bytes, okay? And if there is a relationship between object living in this slice into a young generation, then we are marking this slice as dirty. So this slice has to be checked during the next garbage collection, okay? And this is introduced by some write barrier, etc. But still, we need more, okay? So we are using those generational hypotheses, we are using card tables, but all this stuff is still taking too much time, okay? So they are thinking, okay, so there is a lot of work that we have to do. And it's not a problem that we have to do this work. The problem is that to do this work, we have to stop our application. So it will be great if we will be able to do some work without stopping the applications, okay? And that's something that was introduced by concurrent garbage collector algorithms. About freeing the memory. If we know that this and this and this and this object are dead, now we have to reclaim the memory. And there are two ways of doing that. So those light blue objects are live objects and those are garbage. So we can do something that is called mark sweep, which means I'm marking those objects as dead and I'm sweeping them out. So now I know that there is some free space, there is some free space, there is some free space, and there is some free space. But when I would like to allocate the new object, where should I put this object, okay? To the smallest hole, okay. But still it's possible that I have a let's say, 1 gigabyte of free memory, and I'm not able to allocate an object taking 1 megabyte. Why? Because there is no continuous space for 1 megabyte of memory. Okay, I need a compaction. So there is also something called mark compact. When I'm marking those objects as that, removing them, and then I'm doing the compaction. Then it's great, because to allocate the objects, I just need to do something that is called bump the pointer. So here is start of my free memory. Now it's here, 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 and I'm moving just the pointer, and it's really fast. But to do the compaction, it's really costly and expensive operation. So, as you probably know, for young collections, for young generations in Java world, we are using something that is called the copying algorithm, which looks in that way. There is an hidden and 2 survivor spaces. Okay, so I'm marking all dead objects as blue, and those objects are live. So I'm copying those objects into first survivor space. Then I'm doing it one more time, and all live objects are copied to the second survivor space. And it's great, because there is no compaction and there is no fragmentation. Okay, I have a continuous space. So what is the drawback of this copying algorithm? It needs more space, okay? If you think that the survivor space is like 1 gigabyte, for copying algorithm, we need 2 gigabytes, okay? So we were not able to use it in the whole heap, because we would need to double the heap space, okay? If we are using heaps like 80 gigabytes, it's not so easy to double the 80 gigabytes to 160 just to be able to use the copying algorithm. So the idea of the G1GC garbage collector developers was to split the heap, which means we still are running the generational hypothesis, which means I have an hidden, I have survivors, I have old objects, and something that's called humongous. We'll cover it later. But all the heap is splitted into a lot of small regions, okay? A lot of means that these are between 2,000 to 4,000 regions. And the region size is fixed to be between 1 megabyte and 32 megabytes, okay? So the whole heap is splitted, let's say, into 1 megabyte blocks, which means if we are now working on this, let's say how it looks in action. So all my hidden regions are filled, okay? They are filled out, so now I need to reclaim the memory. So I'm doing a young collection, because it's still the generational collector, which means all those objects are involved in my operation, okay? And now I know that live objects from those regions will be, for example, copied here, as well as from this region. From those regions it will be copied here, and from those regions it will be copied here. Which means I don't need to double the whole heap. I just need to be sure that there is enough space to copy all objects that are surviving the collection. Okay, so now I'm copying those objects. Here will be the new survivor region. Here another survivor region, and here objects are so old that they crossed the tethering threshold, which means they were promoted to the old generation. And now I'm just removing all reclaimed regions. Okay, so as you can see, I'm using here a copying collector, which means there is no fragmentation and no compaction, but I still don't have to play around all those fragmentation issues. Okay, and now, have you ever think about why it's called the G1GC? Okay, so that's a funny situation, because it tells exactly what this algorithm tries to do. Okay, so as you can see, there are a lot of regions, and the major idea behind the G1 is that it's called the garbage first, which means it tries to analyze all the regions that are existing in our heap, check the liveliness information for all those regions, which means in this region there is 5% of live objects. In this region there is 90% of live object, and in this region there is no single live object. Okay, which means that if it's as it's copying collector and it needs to copy all living objects to new region, it's easier to copy one object than to copy 90% of objects in the single region. Okay, so it starts from cleaning the regions that are mostly full of garbage. Okay, so if there is a region which is most likely to have the highest ratio of that objects, then the garbage first collector is starting from those regions. Okay, so now there is something that is hard because we have splitted the heap. Do you remember the card table? It was tracking the references between the old generation and the new generation. And now there is a problem because I want to process my regions independently. But each region can point to each other region, okay? Which means to process single region, I have to scan the whole memory. So that's why they've introduced something that is called the remembered set. That's the first key term of the garbage first garbage collector. And the remembered set you can consider as a sets of card tables, which means that it contains references to all regions that are pointing to my single region. Okay, which means for each region I need to keep the independent card table. And generally it's not that it's free, because the impact of the remembered set is like the footprint of the remembered set is like 5%. Okay, so if you have 10 gigabytes heap, it means that a half of a gigabyte it's used to contain the remembered sets. Okay, so it's generally a lot, and there is a lot of references to process by a garbage collector. So there is the idea that all those remembered sets are processed by something that is called a refinement thread. If you use G1 garbage collector, so minus XX plus G1GC, then you will see that in the thread dump there are a lot of refinement threads. Okay, and those refinement threads are processing those remember set buffers, which means the whole buffer is split into 4 zones. There is white, green, yellow, and red zone. Okay, so if the buffers, the whole buffer is filled for some percentage, then it's in the white zone and nothing happens. Okay, when there are more and more and more references introduced here, then we are entering to the green zone, which means the refinement threads are starting to process those remembered sets. Okay, if there are more and more objects coming to be processed, then we are entering the yellow zone, and on the yellow zone all refinement threads are working to process the buffers. And if it's still not enough, there are more and more objects added to the refinement set refinement buffer, then application enters something that is called the red zone. And this means that application threads are also processing the buffer. So if you assign some object, like I have a variable and I'm assigning the object, okay, or adding the object to a map, this means that your Java code accepts of adding this object has to process all remembered set for those regions. Okay, that is something that you can control because all those zones can be controlled manually, which means all the thresholds can be changed by developers. Okay, so the first and the most important term in case of G1GC was a remembered set. Also, there is something called the collection set or C set, and it's a group and a set of all regions that are going to be collected in the next garbage collection cycle. Okay, and it also introduces some footprint. It's much lower than for the remembered set, but it's still like 1% footprint for keeping all the collection sets. And there is root regions, which means there are regions containing the root objects, and root objects are something that I described when I was talking about the vector algorithm. Okay, so that was a brief look at the G1GC, let's say, building blocks, and there are 4 kinds of garbage collections in G1GC. Okay, normally we used to have a young GC and a full GC, and now we have 4 different kinds. There is young collection, there is something called a background concurrent cycle, there is a mixed collection, and a full GC. Okay, young GC is something that cleans up the young generation, as the name suggests, and it's triggered after filling all hidden regions. So all hidden regions are full. We are starting the young collection. Young collection is still stop the word collection. So in Java now there is no free algorithm of GC working concurrently in the young generation. The only implementation is the Zing collector or C4 collector from Zing JVM from Hazel, but it's a commercial algorithm. So in the normal hotspot, as you use probably on a daily basis, there is no concurrent collector in the young generation. And there are some people saying that G1 is concurrent in young generation, but it's not true. I will describe it later. It's still stop the word collector for the young generation. However, it's divided into a lot of different phases. So when you take a look at the garbage collector logs, and those garbage collector logs for G1 are very verbose, I will show it in the end. There are 5 major phases of G1GC. First is root scanning, which means we are scanning the whole memory to find out the root object. Okay, so leaf threads, parameters, variables, etc., etc., etc. After finding all those roots, we are doing something that is called the update RS. So we are updating the remember sets. So we are processing the remember set buffers that were unable to finish concurrently, okay? Because they are processed by refinement threads, but there are still some work that we have to do with stopped application threads. After updating the remember sets, we are scanning the remember sets, which means that we are scanning all regions that are pointing to our region to do the collection. And after this remember set scan, we already know which objects are live and which objects are dead, so we can start copying all living objects into new regions. Okay, so those objects who survived the remember set scan are now copied into new regions, and after that we are also doing something that is called reference processing. So we are processing all references, weak references, soft references, phantom references, etc. To finish the garbage collection cycle. Okay. After finishing this young generation, our application continues to work, and that's great. But there is always a but. There can be a problem that, okay, young generation is cleared, but we are also promoting some objects to old generation. Okay, so now we have to think about cleaning also the old generation. And the old generation collection starts by something that is called a concurrent cycle, which means if the heap is filled in 45%, it's also something that you can change by the JVM flag, then we are starting the concurrent collection. However, concurrent collection is piggybacked on a UseG1GC. Okay, do you know what piggybacking means? Yeah, it's when you take your child on your arms and you are, like the child is walking on your feet. Okay, so your child is using you to travel. So it's the same that garbage collector does. So it's not doing an initial marking. So it's not scanning the routes, marking all initial objects, etc. It tells young collector to do that. Okay, so I'm an old collector and I need to do something that's called initial marking. So young collector, could you please do it for me? And young collector say, yeah, cool, of course, I have nothing else to do, so I will do it. So it's piggybacked on a UseG1GC. So every time when the G1 decided to clean up the old generation, it starts a young generation collector, and it is looking for easiest regions to clean. Remember, garbage first. So we are checking the liveliness information and we are choosing those regions which are mostly full of dead objects to be processed at the beginning. So the concurrent cycle phases are initial mark, which happens during the young generation pause. After that, we are resuming all application threads, and we are starting the concurrent root region scan, concurrent marking, and remark. Okay, which means that here I'm doing the whole marking of all live objects. So I'm traversing the whole object graph to mark which objects are live. Okay, and of course the application is still changing those objects. So great. Those objects are live, okay? I've marked them as live, but application is still changing the objects graph, which means that at some time I have to stop the application threads and do something that is called a remark. So now I'm marking all objects that it's possible that they have changed during those concurrent cycles. And there is something called the snapshot at the beginning algorithm. If you are interested, you can read about that. That is used, and here we are just processing this snapshot at the beginning buffers. And after that, we are doing some cleanup. If there are some regions that are full of garbage objects, which means there is even no even single live object in this region, it will be cleaned in this phase. And that's something that finishes the concurrent cycle. And now, the most interesting thing in the whole garbage G1GC is that there is no something called old generation collection, which means G1GC is using mixed GCs, which means that you are starting just a new young generation collection, but it's not a young generation collection, it's mixed generation collection, which means that we are processing the whole young generation as it was, it would be normal UseG1GC, but also we are processing some part of the regions which were found and suggested to be cleaned here. And if we have found, let's say, 100 regions, we are dividing the whole region size into 8, and the GC will run 8 mixed collections, one by one by one by one, to clean up the old generation. So there is no such thing as old generation collection. We are cleaning the young generation, and by the way, we are also cleaning some small part of the old generation, this part which has the lowest liveliness for each each regions. Okay, those information about minimum and the maximum number of objects is something that you can control also by the GC flags. Okay, and there is one more thing that is called a full garbage collector. Okay, there is a difference between old major collection and full collection. Major collection is used to clean up the old generation, and the full collection cleans up everything. So metaspace, code caches, etc., etc., etc. And the bad news is that for G1GC, the full collection is the same as for the serial GC. Okay, so it's really, really slow. It can take, for example, if you have a heap of 20 gigabytes, the full collection can take 15 seconds, 20 seconds. So it's horrible, okay? So it's even not parallel. It's one thread collector, which cleans all the stuff. So the most important thing about tuning the G1GC is to fully avoid the full collections, which are, for example, collecting the metaspace. So if you are allocating a lot of objects into metaspace, you will probably have a real serious issue with the full collections in the G1. Okay. Have you remembered the object layout, the heap layout? There were 4 kinds of objects: the hidden, survivor, alt, and humongous. And what are those humongous objects? If object size is bigger than half of the region size, it's treated as a humongous object. Can you give me an example of such big objects in Java? Like they have 1 megabyte, see the single object, 10 megabytes, a gigabyte. Okay, can list or set be such giant object or no? Exactly. The problem are arrays. Okay, the normal set, hash set or something like that, it's pointing to other objects. But if you have for example, array of bytes or arrayed by ints, so the primitive, it's allocated into a continuous memory slice. Okay, so all arrays are probably the humongous objects. And for humongous objects, there are several problems. One is that they are probably allocated outside of the TLAB, because TLAB is too small to keep the whole array in the TLAB. So that's the first problem. But also, there were huge problem a few months ago that if you would like to reclaim the humongous objects, it was done only during a full GC. Which means if you are using a lot of arrays, then you are the G1GC was doing the full GCs all the time. Okay, so there is one good advantage and one good thing that you can do to avoid humongous objects. It's changing the region size. If you know that your application have a lot of objects for which are size of 1 megabyte. Okay, if you will have a region size of 1 megabyte, it will be, all those objects will be treated as humongous. If there will be 2 megabytes, then, you know, if it will be a little bit below 1 megabyte, then it will be normal object. A little bit above the 1 megabyte, it will be humongous object. So for a lot of 1 megabyte objects, just keep your region size around 4 megabytes, and you will eliminate all those humongous problems that are caused by G1GC. Okay? Now, regarding the G1GC tuning, G1 is designed to be really easy tunable, which means it's something that you are tuning for latency. Okay, so there are 2 different directions of tuning. First is the throughput, second is the latency. Okay, so G1GC is a low pulse collector, so we are tuning it for the maximum pulse time. And in theory, it's enough to set the max GC pulse millis into some value, and G1 will auto-tune to keep those to those targets. Okay, so that's the good side of the G1GC tuning. That's the bad side. Okay, so generally it's still a pretty young collector. So it's still being developed, evolving, etc. So there are a lot of non-standard use cases that this garbage collector cannot auto-tune to. Okay, so if you are using some application without some standard approaches, then you will probably have to use a lot of those flags to tune it to run smoothly. And as you can see, there are a lot of those flags. So the good practices. The first thing is that if your collector is starting too late, which means you are not able to finish the whole work concurrently because you have started too late, your allocation rate is too high, you can always lower this initiation heap occupancy percent to, let's say, 40%, 30%, to be able to start the concurrent marking cycle earlier. If it's starting in the right moment, but it's not able to process the whole heap until it's filled, then you can change the number of concurrent GC threads to some higher level. Okay, so it will have more threads and it will be able to finish its work faster. And G1, as its copying collector, it's working much better when it have a lot of free space around. So this space can be controlled by us by changing the G1 reserved percent. If you will change it to 20 or something like that, G1 will try to keep 20% of the whole space free, just that it will be able to copy new objects or surviving objects into new regions. And the last thing that should be turned on by default, and I have no idea why it's not default value, it's that you can turn on the parallel reference processing, which means all the references processed by the GC are generally processed by a single thread. You can turn on the parallel processing, it can reduce your collection times by a factor of 2 or 3 or something like this, especially if you are using a lot of caches, there are a lot of weak referenced objects or something like that. Okay, so is there something else that we should care about when we talk about the G1GC? Yes. G1 is working concurrently with the application, which means the application is creating new objects during the garbage collector is still working. Okay, so there could be a situation that JVM has allocated all objects, there is no free space, and garbage collector hasn't finished the concurrent cycle. So what now? Then the garbage collector needs to stop the whole application, all application threads, finish its work with stopped application phases, so the stop the word phase, and after cleaning the memory, it's resuming the application. Okay, so if you see something like this, then it causes the big stop the word pauses in the application, so we should avoid concurrent mode failure by starting the work earlier. Also, there can be something that is called the promotion of the evacuation failure, which means it's also called as a two-space overflow, which means, okay, I have finished the young collection, but there is no free survivor regions to which I could copy my objects. Okay, so garbage collector now has to allocate new survivor regions to be able to process the work, and there is similar event called evacuation failure, which acts for the old generation. Okay, and when you think about analyzing the GC logs, because I've shown you some really basic good practices, but how do I know that there is a problem, for example, with reference processing? That reference processing is taking, for example, I don't know, 50 milliseconds, 200 milliseconds, 5 seconds, okay? So you can dig into the logs. And garbage collector are logging all the time, but for G1GC, as you can see, those logs are very verbose, especially that it's the average level. Okay, there are 3 levels: fine, finer, and finest. This is the finer level, so it's equal to print GC details. It can be much more verbose by using the finest level. Here you can see all the phases, like remember the root scanning phase, the update remember set, scan remember set, object copying, etc., etc. All those phases are here. Here is the information that we have reduced the size of the Eden from 172 megabytes to 0. Survivors hasn't changed, and the heap was dropped from 2 gigabytes to around, I don't know, 40 megabytes less. Okay, there is times it was taking 2 seconds of the user space, but it was run in a lot of threads, so the real time was 0.2 seconds. Okay. As you probably notice, it will be hard to analyze those logs, especially if there are dozens of collections per second. So are there any tools that you can use to analyze G1GC? Yes. The good news is that old but still good GC viewer is working correctly with G1GC, so it's able to read the logs and produce you the information about the allocation rate, about the pauses, etc., etc., etc. It's also working with the visual VM as well as mission control. Mission control is a great tool for analyzing G1GC. Be aware of one thing, because as I said, there is no something called the old generation collector, but there are some tools that are treating the mixed collections as the old generation collections, and there are some tools treating only the full GCs as old generation collectors. So for example, when you use such monitoring tool as New Relic, it will show only the full GCs as old generation collectors, but it's not true, because mixed generations are also cleaning the old generation, but it's something that you just have to know about. Okay, so is G1GC something that has to replace all other garbage collectors? No. Still, the best garbage collector with the highest throughput, the best performance, is a parallel collector. Okay? If you just have to do some bunch of work and finish this bunch of work as soon as possible, then the parallel collector is the best solution. Of course, let's say that you are running some background job. This background job takes 24 hours. It means that the parallel will have the biggest throughput, but also it can pause your application for 1 hour, clean up the whole memory, and then resume it. Okay, it's not acceptable when we are talking about the web applications. Can you imagine pausing the application for 1 hour to do a garbage collector when users are still waiting for the results? It's not something that we can do. So the G1GC is going to replace only the concurrent mark sweep collector. But if you are already using the CMS collector and you have tuned this CMS collector and it's working pretty well, then don't change it to G1GC, because it will be probably worse than well-tuned CMS. And there is also coming something that's coming from Red Hat called the Shenandoah. Shenandoah is the new approach to garbage collector. They are going to introduce a low pulse collector, which means they are willing to have pauses below 10 milliseconds for each 100 gigabytes of heap. That is something that is outside of the control of G1GC, but it will be probably able to you will be probably able to achieve that with Shenandoah. And the last thing, will it stay default for JDK9? So that's some chat from guys from the garbage collector user group. So as you can see, they've already decided to make G1 default. But still remember about that G1 is designed for big heaps. And it is now in JDK9 default for all heap configurations, which means for 500 megabyte heap, the JVM is still using the G1GC. Of course, the minimum region size is 1 megabyte, so there will be no 2000 regions, only 512 regions. But probably it will behave not as well as for a parallel collector, throughput collector. So please remember about that it's not the best solution. It's great for web apps using, let's say, heaps of 8 gigabytes, 12 gigabytes, 20 gigabytes. But for smaller applications, for microservices, it's usually the bad idea to use G1GC. And that's all. If you have any questions, now it's the right time. I think we have 2 minutes for questions. No questions? Okay, so if you will have some more questions, just I will be walking here. Also, catch me during the beer break. And that's all I have for today. Thank you very much.